Zhiboedov, visiting us from Harvard, and I'm not going to try to pronounce his last name. Go ahead.
Thank you very much for the opportunity to speak here. I will be talking about a recent paper with Shanka, Max, Vasilios, Stein, and Juan Aldacena. The paper is about causality constraints on the 3-point Graviton coupling. So let me start by explaining what the 3-point Graviton coupling means, because this notion depends on the type of spacetime we are working on. Let's say if we work in flat spacetime, or asymptotically flat spacetime, then it's 3-point scattering amplitudes between gravitons. It's a physical observable. It depends on polarization tensors and momentum of the gravitons. Now, if you're more used maybe to ADS, HET, and physics in ADS, then the physical observable, which is again gauge invariant and independent of any filter definitions or gauge, is a 3-point function of stress tensors in a dual CFT, or if you wish, it's 3-point function of graviton scattering in ADS. And in de Sitter space, or asymptotically de Sitter space, it's a gravity wave spectrum non-Gaussianity. So it's a natural observable in this case. So this is an object that we will consider. And we will be interested in theories which are very, very weakly coupled. So it's very important to remember that Newton's constant is very small. So it's always effectively tree level. We assume that there is one coupling constant that governs loops. It's G, and it's very small. So my talk is about, if you wish, classical gravitational theory. It's very important. Well, of course, we know that very well at large distances, physics is described by Einstein's theory, and it governs physics at large distances and low energies, and it has potentially some corrections. And we would like to consider a class of theories with the following property. It's a theory with high derivative correction, so we add something like alpha r squared in quotes. By this I mean that it can be whatever invariant you can build a Freeman, Ricci derivatives, whatever you want. And plus, again, infinite series potentially of corrections. Alpha, of course, it's a new scale. It has dimensionality of length squared. And in principle, if you say maybe effective field theorist, you can say, okay, there is a coupling constant, so we have expansion in m Planck. So this alpha is of order 1 over m Planck squared. Yes, this is true in some theories, and definitely this can be the case. But we will be interested in a different regime, or a different type of theories, where m Planck is much, much larger than 1 over square root of alpha, or equivalently, square root of alpha is much, much larger than L Planck. So that's a regime. So you can think that m Planck is very high, and here we have some intermediate scale given by the square root of alpha.
The string coupling is weak.
Yeah. The string coupling is weak. So, of course, you can say, okay, what kind of theory? It's in a sense, it's a theory at intermediate scales. When we start doing physics at the scale alpha, we are sensitive to these high derivative terms. And a famous example of this type is string theory. Exactly. So in string theory, this is exactly the type of thing that happens. And alpha is identified. So an example is when square root of alpha is equal to the string scale. This is a famous example.
But that doesn't mean it is large compared to the first term. In the zero slope limit of string theory, we can continue to ignore them, right?
Exactly, but well, so there are different. So you can take zero slope limit, and zero slope limit will be very different from this, because we will have a tower of all states. Here we consider more realistic scenarios like our universe where we don't observe high-speed particles. So if they're there, they're very heavy. Maybe so this scale is small because, well, there are some experimental bounds on this type of corrections, but they're small. And now, in string theory, there is a second thing that happens at the same scale, which is a priori, this could have not happened. What happens is that at the very same scale of alpha string, we have an infinite set of new states of all spins. So this happens in this example. Because again, we have oscillation modes of the string and they occur at the same scale. Now, the questions that we would like to address in this talk is it a generic feature? What do I mean by this? Well,
Excuse me, before you go on,
Yeah.
if you only consider this as an effective field theory, and look at its spectrum, so they have only one massive spin 2.
there is only graviton here. So
And
I
then
start
a massive one as well. Yeah.
Well, I'm starting with a effective theory for the gravity.
Mm-hmm.
Effective theory for gravitons, tree-level graviton asymmetrics. And then we discover that at the same scale, we have all kind of other states.
But not in this theory, in string theory.
In string theory, yes.
Not this one,
Right,
it's
but-
defined
but-
as an
but-
effective theory.
No, but imagine we measure graviton scattering. We do not have direct access to high-speed particles.
Yes.
Then we will see this kind of thing. But then we will discover that there are new states.
Okay.
That's what happens, yes. And when we ask, is it a generic feature? So on one hand, we have corrections to GR, and we have new states. And we would like to provide the link. Notice that in principle, one has maybe you can say you can argue that okay, when we reach a Planck scale, this theory is not good. There should be a whole set of corrections, new states. But what we would like to argue is that new states should appear at a much lower scale. Theory is completely weakly coupled, and the idea is to try to argue that this theory is pathological unless there are new states. This is the idea. So we would like to argue that, the way is the object of the interest will be three-point coupling. Three-point coupling because it's the simplest observable, which is on one hand is insensitive to. Well, on one hand it's simplest. On the other hand, it's a simple thing that is sensitive to this kind of things. And the way we would like to provide this link is using causality. So the idea would be to show or to argue that if you have a theory of this type, if you don't have new states, and let me emphasize again, we always assume that it becomes weakly coupled. It can become strongly coupled. There can be theories of different sorts, but if you would like to have this theory weakly coupled, and you want it to be causal, then we would like to argue that any correction that changes three-point coupling of GR should come with new states at this scale. Moreover, these new states, it's an infinite number of high spin states.
Just to make sure I understand this,
Yeah.
so you're assuming that the ghosts will not be a problem with this?
Oh, so if you wish, we can take an on-shell point of view. So we observe the low energy spectrum. We have a graviton. Then we can scatter gravitons and study the scattering of gravitons. So there is no, well, if you wish, we assume that the theory is good. We have only graviton and low energies, and then we start studying scattering of gravitons and would like to relate this scattering to new states in a theory. And we would like to.
But the ghost that won't show up at the Planck scale, you assume
Oh
it
no,
will
yeah,
only
we
show up at
never approach the Planck scale. That's
And you treat R squared terms as interactions.
yeah.
Regardless of whether it is Riemann square or Ricci square, doesn't
Yeah, no,
matter.
in general, if you want to study particular theory, you can take a particular theory and do this experiments that we're doing. But the nice thing about this 3-point coupling is that it all will be fixed by symmetries.
Okay.
So we don't have to worry about particular. Now, let me say about, the
And this statement holds for all three cases that you draw over there? Higher spin states. That picture emerges from all
Well,
three.
actually, as I will explain, so these two cases are very similar,
Mhm.
and it holds for both these two. In this case, we do not have intrinsic formulation of causality in the series space, but if it has a nice flat space limit, well, actually these two cases will be sort of related to flat space. This is a little bit better related because you can define this in anti-de Sitter space, but the conclusion that you have these new states, it, at least under these assumptions, holds in all three cases. Well, now let me briefly say motivation. We would like to understand, say, landscape of classical gravitational theories. And of course, another thing is to understand how unique is string theory. Well, the idea is you see here to kind of try to get a string-like structure just from very general principles. So we take causality with coupling and some corrections and see all these states of higher spin particles. So, and also I think the important point is that, which I will hopefully explain if I have time, that theories with massive higher spin particles, which are importantly massive, look quite robust. Which are robust on the question, how robust are they? What can be said? I think it's a very interesting question because there was a lot of study of massless particles, but we don't observe them, obviously. Though these kind of arguments, they suggest that even if they're very massive, if you want to make them causal or well-behaved in some sense, you have to work hard. And I think there is no, if you do explicit example, there is only one example of string theory where it actually works, as far as I know. So that's the motivation. Now let me describe, the first will be flat space, and let me describe a setup of what we actually do. So the idea is, if you wish, a modification of a classical work of Shapiro, who considered the famous paper force test of general relativity, where he suggested the following setup. You have a planet, Earth or Mars, and you have a sun, and you send a radio pulse, it bounces back. This is sort of cartoon, but the point is that then you look how Mars passes the sun and you measure for the delay of the signal when it comes back. And this is a correction which you can compute in general relativity, and the result of this Shapiro time delay in d dimensions, this has roughly this form. So G is a Newton constant, M is the mass of this planet, and B is importantly impact parameter. So B, it's a minimal distance between this trajectory and the sun. And it's called delay because it's positive. And you see that this positivity of the delay is related to positivity of the mass. And this mass becomes negative. Many things go bad. Now, we consider generalization of this experiment in several ways. So first, delta T Shapiro being positive or negative, it's related to causality, as I'll try to explain. So you better have always causal. And this will be what we'll be imposing. Now we also consider a relativistic version of this experiment. We also, it's absolutely crucial for this talk, consider polarized particles. The fact that graviton carries a spin. In this experiment, well, in the original experiment, this was an electromagnetic wave, but polarization didn't play any role. So here we consider a setup where the probe is polarized. So remember that everything I'm saying here today, it's for particles with spin. And the fourth difference is that you can sort of bootstrap this Shapiro time delay. And by bootstrap, I mean that you can compute it in a generic weakly coupled gravitational theory without ever talking about the action. So as I will try to explain, this Shapiro time delay is related to 3-point coupling, and 3-point coupling is completely fixed by symmetries. So we never really don't need to talk about action or.
But you started by talking about action.
It was just an example. I think it's maybe at the end I will write the formula for this thing as a function of 3-point couplings, and these 3-point couplings are physical parameters of the theory. Say 2 of them are 0 in GR, and as soon as you turn them on, we will run into a problem. That's the idea. So any questions about this? I will then go to flat space and describe this spin relativistic generalization of the experiment and compute the delay. Okay, so now to make a planet relativistic, we can boost it. So, and the geometry of a very fast particle, relativistically, a particle moving at the speed of light, is known as a shockwave geometry. It has a very simple form, so consider Minkowski space. And then we add a direction which depends on the transverse space. And so this is just flat space, and this H is due to a particle source which is localized on the light cone. So if we write Einstein equations for this kind of geometry, which has a source localized on the light cone, it takes the following form. It's just a Laplacian in the transverse plane, just G minus 2-dimensional, acting on H. It produces the source. The source is delta function, say in U, delta function in X, it has G here, and it has a momentum of the particle.
Can you comment on relation between this metric and the so-called PP wave?
Well, it's the same. It's only for PP wave you consider you consider 0 here. So if you consider 0, you'll get a plane wave.
Meaning in that function H you have only
Yeah.
X dependence or
No, in
U
the meaning
dependence?
that here, so the kernel of this thing is like X and constant. So it is a solution which is for which you don't consider a source. So here we have a source which is this particle. Okay, so the solution of this equation is very simple to write. It's just G du R G minus 4, where R it's a distance in the transverse plane. So that's a very simple geometry. Now let's consider the following experiment. We take this solution, and yes, and importantly, it's also localized here on the light. Sorry. Now let's consider this. What happens? And this is the role of the sun. Now let's consider the probe. Well, the probe is what happens if we send the probe. Let me draw the shock wave. So we have U, we have V. So you see the shock is localized at U equal to 0. And we have a transverse plane. So let's say we have a shock. And we have a probe localized. And they're separated by V. Now if you send a probe, there are a couple of things that happen when it crosses a shock. First is this delta V. And second is deflection in the transverse plane. So if something was moving, it gets deflected or attracted when it's just gravitational attraction. But deflection will not play any role because you can always make a setup where there is no deflection. For example, if you put a second shock here, then there is no deflection, but time, this shift will stay. So we'll focus on this shift. And if you compute this shift, it's the result will be G U B T minus 4. And this is nothing else as a Shapiro time delay. It's the same. Instead of a mass, we have an energy of this particle, which creates a shock. So that's this is
But how do we know what gravity theory has this solution?
Great. So one of the properties, first of all, at the end, I won't talk about shock waves, but I think it's a nice picture. But a nice thing about shock wave solution is that whatever action, say if you write any action, it is always an exact solution. And this is the fact. Well, this geometry has a covariantly constant null killing vector. So if you write a Riemann, it has this form that if you try to write some equation of motion, say R mu, and if you try to add anything, it will either be 0 or it will be the same. So it's an exact solution in any at least whatever series you write, it will be an exact solution. It's a nice geometry. It would be nice to understand it as in Vasiliev theory, for example. Because it's like the simplest thing you can do, and it seems to be seems to always exist, but maybe in Vasiliev theory it's okay, so this is this relativistic version. So I tried to explain this. Now let me explain why it is related to causality. For example, and I think I will draw a cartoon which is supposed to illustrate why you don't want this to become negative. Why, if it becomes negative, it's something goes wrong. And you better impose it as positive. So consider two shock waves now. Now they're localized around U and V, but they're very much separated, say, in transverse plane. So this is the transverse plane. And let's send a probe, and we send it as follows. Say, let's start with here, and it's relativistic probe, but because it's, let's say it moves in the transverse plane. So this guy is a probe. Now imagine that we come very close to the one of the shocks, and we cross, and we allow ourselves to jump backwards. So we jump backwards, and then we go here in the transverse plane, and here we again jump backwards, and so we form a closed time-like curve. So we better don't jump backwards. That was an illustration of why Shapiro time delay is positive, if you wish.
How do I see its negative time delay in that diagram?
Well, because the time delay here is this is delta V. And when we cross, we go backwards. So here.
Oh, I see.
Yeah. And similar statements, or maybe much more rigorous, been well known in general relativity. For example, there is this paper by Gao and Wall talking about time delay, and they prove rigorous theorems about where they try to define rigorously this kind of notion of not jumping backwards, and they prove that if in general relativity null energy condition holds, then what is so-called asymptotic causality holds, which is simply the statement that if you have something happening in some region of space-time, then the causal structure far away is not distorted by this. So if you start with Minkowski space and you stay far away, so if you say if you have two events which were sort of null separated, and then you add something in between, by going through the middle you cannot get faster to the boundary. And I think this is especially sharp in ADS, where if you take a boundary of ADS and you take two operators and you take some state, you know that in a sort of the way you impose a causality is that commutator of two operators in any state is zero if these two operators on the boundary are space-like. So this notion that the causal structure far away is not affected by whatever is happening in between, and we would like asymptotic operators commute. That's a causality condition we would like to impose. And here, this is exactly the same. If you consider Minkowski space, these 2 points are time-like separated, and these 2 points are space-like separated. So you don't want to send signals to space-like separated points. And we would like this asymptotic causality to be a property of any gravitational theory. So this is, if you wish, an assumption, or we would like to impose it on any theory. So this is a relation between Shapiro time delay and causality. Now let me make this experiment.
For you, the only observable so far are the 3 entities, Graviton scattering entities.
Yeah.
Do you have any other possible observable you can think of?
You can scatter light, for example, or uniform. Well, I think the type of constraints that we will get is only non-trivial for particles with spin.
I see. But your space-time will have trivial topology, so there won't be some strange states.
Well,
non-trivial global properties, say.
Yeah,
No.
here we consider
Strictly perturbative waves they are considering, and they're scattering.
right. We consider classical scattering, so any black holes or nothing complicated happens. So
No black hole physics here.
No black hole
Okay.
physics. Yeah, no black hole
Okay.
physics. So, okay. Now, if there are no questions about this general idea, I would like to consider the same experiment, but for particle with spin, and see what happens. Well, first of all, if you do scattering with polarized graviton and GR, you will get exactly the same answer. So nothing depends on spin in general relativity. But let me repeat this experiment in a famous or simple theory, which has higher derivative terms, and that can illustrate the basic point. And this theory is that I would like to consider. It's Gauss-Bonnet theory. So we take R and we add lambda Gauss-Bonnet times Riemann squared minus 4 H squared plus R squared. And this is in d dimensions. In 4 dimensions, this term is topological, so d larger than 4. But it doesn't matter. It's really just an example to show the main point. Now, first of all, as I said, that in any theory of gravity, this is an exact solution. Same is true for this Gauss-Bonnet theory. But if we now consider this probe being a graviton in this theory, there is this. Yeah.
So it's an exact solution without source terms in the action?
Oh no, this is a yes, this is a source term.
No, I mean in the action. Like in order for that to be an extreme of the action, including the source. There's no, if I plug that into the.
Well, I think if we add here say scalar field and consider the TAMU being a stress tensor, this is an exact solution. Now, let me consider this probe graviton based on delta H. And the equation, if you make this exercise, compute the equations of motion for a probe graviton in this geometry, you get something like this. Okay, so H is this H, and delta H is a perturbation. This equation, and here there is this lambda Gauss-Bonnet. First of all, if notice that this equation is an equation which is valid in high energy limits, so we consider this graviton to be very energetic. And if you drop this lambda Gauss-Bonnet term, if you set it to 0, this is a wave equation which, if you solve, you get this effect, delta V. So this is, here I showed you the exercise for geodesics. Of course, it's the same for the waves. If you do a wave equation, it's the same as doing geodesics. So when lambda is 0, it's this discussion that we had there. Now the basic fact about this higher derivative corrections that gravitons do not follow geodesics anymore. And you see that this extra term appears. And moreover, this term has non-trivial polarization structure, so it's polarization dependent. By this I mean that here, I'm sorry, I should have written delta ik. So in general relativity, the transfer is diagonal. So you take Hij and it's still Hij. But in this Gauss-Bonnet theory, you will have some non-trivial structure in polarization space.
How did you get to the derivative term from Gauss-Bonnet? I thought Gauss-Bonnet has the famous feature, I thought, that is exactly the combination which avoids introducing two derivative corrections to Einstein.
Yes, so you see that
but that's exactly what you've written down.
No, I thought so. Gauss-Bonnet is famous that if you take some background, the equation for perturbation is second order. As you see.
Exactly.
Yeah. So it's second order. So it's second order, and this term it's multiplying H.
Oh, it's quadratic. I'm sorry.
Yeah.
Okay. This interaction term you've written. Sorry.
Right.
Okay.
Right.
Okay.
No, it's absolutely
Thank you.
correct. Yeah. From this equation, we can compute this delta V, and the result is that it's equal to let me explain what this formula stands for. So this formula stands for this shift. 1 corresponds to usual delay. Now we have a lambda correction. And importantly here, I introduce epsilon and n. Epsilon is polarization of the graviton. And n, it's we have this vector in transverse plane, which is the impact parameter. So if you write E as E times a unit vector, we have this E times n. Now, well, this term is the same as, it's a result of having this polarization dependent thing, and you see that if you polarize your graviton so that it's transverse to M, you get something, and then if you polarize that it's aligned with this M, you get a different result. That's the first thing, so it's polarization dependent. And the second thing is that having these extra derivatives introduces 1 over B factors. So you see, even when B becomes small, this correction becomes more and more important. Moreover, by choosing polarization appropriately for any sign of lambda, this guy is negative. So by scattering close enough in a transverse plane, you can get that delta V is negative for B of order square root of lambda Gaussian.
Sasha, I'm sorry.
Yeah.
So there's this, a few years ago, I'm sure you know, you and Rob Myers, a company were
right.
looking at causality.
Exactly, yes, yes.
So what is, I mean,
What's
they
the
were,
difference?
yes, what's the difference?
Yes, so the difference is that the result is that lambda Gauss-Bonnet is less than a number. Now, this is an experiment which shows that whatever lambda Gauss-Bonnet is, if you don't have extra states, you have a problem. They have that lambda Gauss-Bonnet in 5 dimensions is less than 9 over 100. Here, if for any lambda Gauss-Bonnet, positive, negative, well, if you trust the computation, and there are no extra states, this is where the computation is trustworthy.
Where do they get that constraint?
They consider EDS black hole in EDS5, and they send a signal, which in EDS, and then they impose that signal length inside a light cone on the boundary. So they're doing same boundary causality, but in different background, if you wish.
And it can be negative number as well. It's just less than 9 over 100.
Yeah. So they have just a number. Okay, so this the discussion. The bottom line of this discussion is that there is a problem with this theory by itself for any lambda, and well, you can say that okay, this theory I'm not interested in, and because you can say this, let me reformulate everything so that it's completely independent of any action and solely depends on 3-point Graviton couplings. But the basic problem is this with this hard derivative theory is that by playing with polarization of the graviton, these hard derivative terms introduce negative Shapiro anti-lane. This is the bottom line of this discussion.
How does string theory avoid this?
Yeah, that's I will hopefully have time to explain. But the basic point is that there are extra states. Now, if you have so this interaction with a graviton, it's basically a graviton exchange. So what we are doing is this is, if you wish, is a shock wave. This is a probe, and they interact through gravity. Now, if you have extra states, in string theory, this is exactly what happens. If you compute the delta V, there is this term. So okay, you say you are running into trouble. But what happens is that if you have in your theory extra states, let's say with mass m, then the effect of this extra states, it has a factor e to the bm in it. So exactly, and m is related to higher spin states. String theory avoids this because this computation breaks down because you have to include extra states. And that's how, that's a basic idea we would like to exploit. But let me be more maybe precise and explain how it happens. So not to think about the action, we would like to reformulate a problem in completely on-shell terms.
Sorry, can I ask another
Yeah,
question?
sure.
About the polarizations, so if you decompose H mu into which one is, can you pinpoint which one is causing the trouble? Is it
This
just
one, it depends on what sign of lambda. You see, if you choose it, say, being positive, then the problem will come on this guy's negative. If you choose it to be negative, the problem will come from when the bracket is positive.
Sure,
So-
but which
Yes,
polarization?
so the polarization is that you have to consider two types of polarizations. One is when epsilon ij and I is 0. So when graviton in the impact parameter space is orthogonal to this. And this is problematic if lambda is positive. And you consider epsilon ij
So
and
those are, the first one is the shear, is that right? Or, I can't remember what they're called.
I'm not sure.
Okay, no.
But there's a case where you don't need epsilon. You don't need polarization even. If lambda is positive,
Yeah.
if epsilon is 0, still it can be engineered, I guess, right?
Well, epsilon is never 0 because epsilon is polarization, right? We have to pick it.
No, but if you did this experiment,
Yeah.
oh, you have to have some epsilon.
Yeah, we
Then
have to
stand up
polarize
there.
it somehow.
Of course, of course.
Yeah. So
Which dimensions is this?
any dimension larger than 4 here.
Larger than?
Right, but what I will try to tell you now is valid in 4 as well. The problem is in 4 dimensions this is trivial.
Right.
I should say that the numerical factors are all 1 here. So in reality there is d minus 4 here and d minus 2, but it's trivial with 0 and 4. Now we consider a scattering experiment, and let me reproduce this result using scattering amplitudes. Okay, so we had a shock. The shock is 1 particle, and we have a probe. It's another particle. And we are doing something with a 4-point amplitude, scattering amplitude in this experiment. This computation is something with a 4-point amplitude, and this something is a scattering in a so-called impact parameter space. So we have our particles separated in the transverse plane. That's something very well known. People study this. It's known. Say, if you have let's say you have a scalar particle scattering and they exchange a graviton. So now I consider this being scalars again for simplicity. Then it will be very easy to generalize. Then the amplitude is this. I don't know if this probably this familiar formula. This is S. It's a Mandelstam variable. It's total energy, and T is the exchange momentum. If you want to get the S matrix in an impact parameter space, you have to do transform this. It's a momentum space. And this transform, it's just Fourier transform with respect to exchange momentum. So if you take this, and we set T be minus Q squared. So if you do this Fourier transform, which is to go to S matrix in impact parameter space, you will get the result being again the same GS B D minus 4. Well, it's not. This is, I'm telling you, just the result of the computation. If you do take this amplitude, go to impact parameter space, do Fourier transform, you get this result. And now, why is it the same? Well, it's the same because let me write it as an exponent here. Well, this is an expansion of the exponent, but let me assume for a second that it exponentiates, because it will exponentiate at the end. Now, if we have this particle here, it has a wave function e to the I e v v. And now we add a scattering amplitude, which is an e I delta s and b. And because delta is proportional to s, we can rewrite it as an e I b v b minus delta v, where delta v comes from this phase. And if you compare this delta v computed from this phase, it's just again the same thing. But now, this was again to get the same result in a different way. But the important point of this exercise is that if you look at this integral, the way which can be easily done is by deforming the contour in this momentum. And the whole result comes from the pole when this q square is null. And but when you have a pole in a scattering amplitude, by unitarity amplitude factorizes. So actually this result, it comes completely from the pole, which is fixed by product of 3-point amplitudes. So we have one 3-point amplitude, another 3-point amplitude, and then we do some operation on this, we get this result. That's, I hope this was supposed to convince you that you can get the same, do the same computation, and this computation is governed completely by the 3-point Graviton 3-point coupling. That's the idea, and here I hope at this point I should convince you that spin was important, and we can bootstrap it because now we reduce it to 3-point couplings, and let me tell a little bit about this 3-point couplings.
Is that supposed to be exact result in some sense? Or
well, it's exact if you don't have extra states. So if you take your action, gravitational action without extra states, and reduce yourself to tree level, we don't have loops, then this will be the result in terms of 3-point coupling.
in other words, diagrammatically speaking, this result is supposed to add up perturbatively infinitely many diagrams. Where I would take multi-gravitons, but at tree level.
Oh, no. So
no.
I think what happens is that, let's say, this 3-point coupling, it can be sourced by many terms in the action. And to compute this, you can, in principle, work very hard in terms of microscopics. So, but as soon as after you're done with this follows. And intuitively, if you have some complicated contact interaction, it does not contribute in the impact parameter space. Because you see, if you have contact interaction, it's local. And we are considering scattering at fixed separation.
Forgive my question, but if I don't have a Lagrangian at hand, how do I know how to compute this 3-point function?
Great, that's exactly the next step which we will do. How to compute the 3-point function. Now the great fact about 3-point function is that they are fixed by Lorentz symmetry up to a set of numbers, namely 3 numbers. So if you have this 3-point function, it's a function of momenta, gravitons, and their polarizations. You can impose Lorentz symmetry and gauge invariance, and the result is that it is a sum of 3 terms. One is the one you get in Einstein theory. Second one that you get in sort of Gauss-Bonnet-like theories. But at this point, forget about the action. It's just a known function of momenta and polarization. Then there is another term which you will generically get in theories which sort of Riemann cube. And this is completely non-perturbative results because these functions are fixed by symmetries, and these are parameters of our theory. Let me write here square root of g. Now this. So if you take Einstein theory, you compute 3-point coupling, you get the function, etc., etc. So now we can think about theories as parameterized by alpha 2 and alpha 4. These are physical parameters. If you have your particular theories, it can be very hard, but it can be, one have to work related to your theory. So that's an answer to your question. Now what happens is that if we compute this
In ADS, you would have to give me a cosmological constant, of course.
In ADS, yes, well, but I think
That's not a parameter.
yeah, it will in dimensionful, saying CFT for 3.1. It will be always operation. So if you now take this 3-point amplitude and you would like to compute this shift in a generic theory, as I try to explain, the contribution comes from the pole. By unitarity, pole is fixed by a product of 3-point amplitudes, and the result for this shift is the following: so if you take your 3-point amplitudes and you exchange one of the momentum with the derivative with respect to B, and this comes simply because we have a Fourier transform. So if you have a factor of Q, you can equivalently substitute with the derivative with respect to B inside this integral. And this differential operator, which is known, it acts on this basic Shapiro delay. And now this 3-point couplings, these are couplings between external gravitons and the ones that is exchanged, which is on shell, this formula. This formula can be, now we can compute exactly, because everything is fixed in this formula, and we impose that this is positive, this is causality. You can, by looking at the formula, writing the result and imposing that it's positive, you see that if alpha 2 or alpha 4 are non-zero, you run into a problem. So as soon as we correct GR at the level of 3-point couplings, we run into this problem. And this is the basic point and basic experiment which I want to tell you. And the same experiment you can run in ADS and run into the same problem. But let me tell you now, okay, so this theory is bad. So something should happen, like in string theory. We have to add new states to fix this problem. So now fixing the problem. Any questions?
In string theory, though, at least in the flat space case, don't you actually have alpha 2 and alpha 4 being 0? Because that's my point.
Yes, so it's a very good point, because in this alpha 2 and alpha 4, it depends on type of strings. Say in type 2, there's 0, but in heterotic strings, there is 0. 2 is not 0. This is a very important point, because in principle, this, you see, this type 2 string theory is an example of a theory where we have new states, but this argument is blind to it. So definitely this is just the simplest thing you can do. And there are theories like type 2 strings that evade this argument. But I think the moral of this argument is that if you consider more elaborate experiment, you should run into a problem, but it's harder. Well, fixing the problem is, I already mentioned it there, it boils down to adding new stuff, new states. And if we exchange this extra states, what happens is that instead of 1 over q squared, which is a propagator, we will have 1 over q squared plus m squared. Now, if you do Fourier transform of this, you will get a Yukawa potential. And this intuitive thing that if you have mass particle with mass m, it becomes important as 1 over b. Okay, now the thing is that I think unfortunately, I was not able to emphasize it well enough, but it was absolutely crucial that gravitational amplitude behaves like a s squared. It grows with energy fast enough. And the reason is that when we go to the impact parameter space, we have 1 over s, which is just kinematical factor, believe me. It has nothing to do with dynamics. When you transform to impact parameter space, you get. And then we got this s here. Now this s was in our experiment PU times PV, and when we act with this phase shift on a plane wave, we get here PV times something, and we can interpret it as a shift. If your amplitude does not grow with energy, this you just don't get anything like this. So immediately from this you conclude that spin 0 and spin 1 particle, spin equal to 0 and 1, they don't help. Okay, next let's try to add a particle of spin 2, like Kaluza-Klein gravitons, spin 2.
And also being in the spin 1 doesn't have such a problem.
Huh?
Spin 1 doesn't have such a problem.
Yes, but I'm saying, let's say we have a gravitons that scatter, and now we run into causality problem, and we'd like to cure it. So we start adding new states here, and I'm saying that if you add a new state here, it doesn't cure this problem.
And I want to know that if some higher derivative gauge series, like f to the high power, will that have such a causality problem? Looks like
Bornefeld type theory, say. Could that help?
Okay, so sorry, maybe I did not understand. So we consider graviton scattering, right?
Yeah,
At tree level. And we exchange now a spin 1 boson. That's what the set that you have in mind.
Oh, I just want to know that if I just start from a pure spin 1 theory.
Oh no, for spin 1 there is nothing to say exactly because of this.
There are no causality variations.
No. Yeah, no. For spin 1 there is no. Now for spin 2, in principle, you can. I'll try to finish for a minute. For spin 2, in principle, you can expect that there is a way to fix the problem, and well, it's. Our conclusion is that, well, you can play with polarization of a probe, polarization of this shock wave or this other particle, and show that if you're adding spin 2 particles, they actually don't help as well. This is not as obvious as this. You have to do the computation for it. But the basic result is this. And the familiar thing is, well, there is a connection to Weinberg-Witten theorem, you know, in well, okay, I will be very brief. They don't help. And for higher spin particles, they do help. There is another potential problem with higher spin particles, which unfortunately I don't have time to explain, which is that if you add one higher spin particle, then this amplitude, it will scale like S j minus 1. That's a famous formula, where j is the spin of this particle. Now, if j is larger than 2, it's a problem on its own. And the reason is that what happens is that when we act on a plane wave with something like PV, I don't know, to the j to some power, let's do alpha. If you consider now this as a sort of a signal model where you start with a plane wave, you multiply it with a phase, you can see that whenever this alpha is larger than 1, you always run into a problem. And this is basically related to the famous fact, which is that if you have a box, you send the signal in, you send the signal out, you have an S matrix here. What is causality for the signal model? Well, the causality is that in the upper half plane, if you have S of omega, it's analytic and it does not blow up. And if you have something like e to the I omega, say, cubed, you see that there are some rays where it blows up. So higher spin particles, that's why they're tricky. As soon as you add a higher spin particle, your amplitude grows too fast. And then for this kind of reasoning, you will get into a problem, different kind of problem, not this polarization dependent problem, but the problem that the energy grows too fast. And this from this we conclude that it's one won't help. You have to add infinite number of them so that they all sum up into something which is well behaved. And this is what happens in string theory where the amplitude regiizes. So we have an infinite number of them, of all spins. And well, their mass is related to this new scale exactly because of this fact. So we have this exponential damping, and well, now it becomes tricky. We have to talk about spectral density, blah, 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 and we don't have very sharp bounds. But physical picture is that we have to add these particles roughly at this scale. And
you don't have refined data which will tell us a mass formula.
right.
You don't have that yet.
No, we don't have, well, for refined formula, we have to know the spectral density of these high-spin particles. And I think that's a problem on its own. Let's forget about all this, take a theory with massive high-spin particles that, for example, impose that it has a tree-level amplitude, which does not grow too fast at infinity. And I think this sort of problem, maybe it has a solution which is only Veneziano type amplitude, for example. Where we do not know about microscopic theory, we just say that the amplitude has only poles, it is crossing symmetric, and it decays and behaves well at infinity, it does not grow too fast. Maybe the only solution is Veneziano, I don't know. This is a complete, the whole...
But then you verify string theory. I mean, how can you find alternative to string theory?
Well, I'm saying that maybe if you want to, yes, the idea is that under this assumption, it will be unavoidable, string theory. That, well, maybe in reality theory becomes strongly coupled, maybe 3-point coupling is not corrected, but if you stay in weakly coupled regime and you modify 3-point couplings, then you end up having string-like theory. And so maybe that's the only theory which with these nice properties. And well, we don't know any other examples. So I think it will be very hard to, it will be very interesting and probably hard to cook up an example, which is not string theory and which of this class because of this argument. Now, let me quickly say, this is a basic conclusion of this fixing the problem. It boils down to the same kind of bootstrap. All 3-point amplitudes are fixed. So we add any particle, we can compute its contribution, and we impose that it's positive. That's the game we play here to analyze this thing. Now in ADS, it's exactly the same story, almost. You can compute, you can do the same computation. Well, this formula becomes more involved because the space is a little bit more involved. But the shock wave is still an exact solution in any gravitational theory, even in ADS. That's a nice thing. And the problem stays the same. So we have this thing being negative or positive, and we have to add new states. And the formula for delta V in ADS, it nicely interpolates between, so delta V ADS, it interpolates between this Hoffman-Maldacena bound. Maybe you heard the bound on A over C comes from positivity of energy correlators. And it goes to flat space bounds. So if your particles in ADS scatter at small impact parameters, like flat space, at large, formulas reduce to Hoffman-Maldacena. And the result, the conclusion for ADS type theories, I think formula may be familiar to people also, that A minus C over C should be bounded sort of by the gap of the theory.
That operator has no spin, I remember.
Sorry?
The delta is the dimension of spin zero operator.
Delta.
You can bound A minus C.
This?
Yes.
Okay, so this is an operator.
Without
It's a
spin.
single trace operator
Yes.
of spin 4
Spin 4.
or higher. It's a higher spin one. And for example, in n equal 4, it's easily saturated because in n equal 4, gap is 4 squared of lambda, but A is equal to C. But in general, this is the physical meaning of this bound is that there is this general law, which is nice to prove that when your theory is gapped, it's described by purely Einstein theory. So this is in this direction. And in the Sitter, it's again fixed by symmetries, and the analogous computation is gravity wave non-Gaussianity, and which actually this correction could have been quite large during the inflation. If I know if Hubble during the inflation was 10 to the 14 GeV. So then if all this assumption hold during the inflation, you again would conclude that by measuring this gravity wave non-Gaussianity, you should link them to the string-like states during the inflation. Under this assumption, maybe this assumption is completely had nothing to do with real inflation, and the theory was not weakly coupled, blah, 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 blah. But the nice thing, again, is that you can do computation based on symmetries, and you can relate this as first non-trivial observable for inflation, which is gravity wave non-Gaussianity, well, not a scalar one, because we have to have a spin, and relate it to some extra states. So the conclusion is that I try to explain an example where having a weakly coupled gravitational theory, one can find a problem at this intermediate scale with causality. This problem was crucial, that we crucially used spin of the graviton, and then it was possible to formulate the problem entirely in terms of three-point functions which are fixed. And the conclusion is that if we want to stay in the tree level, we don't want to add loops, then we have to add high-spin particles. So this is one of the examples where you see the role of these high-spin particles in string theory. Why do they appear? Why do they have to be there? Thank you.
Any other questions?
So your argument highly relies on the existence of some intermediate scale. But besides the effective theory from string theory, do you know any other magic theory with where the higher derivative correction appear become important at an intermediate scale, not Planck scale?
Well, I would, I don't know if there are some other problems, but exactly the idea would be to consider Lovelock theory or Gauss-Bonnet theory. For example, as far as I know, if you consider this theory in ADS with some small lambda, there were no arguments that it's sick at this scale. So this would be an example.
Just to mention it, there is a recent paper by Harvey Rial and postdocs in Cambridge where they find the different set of sicknesses.
Right. I think.
In flat space, it's safe. There is no shock wave in flat space.
In their paper?
Yes.
Okay. But in ABS.
Yeah.
So
I've
that's
heard
different.
many, well, some complaints that this theory is sick in different ways.
So if I tune the coefficients of lambda Gauss-Bonnet to be at the Planck scale, then
Oh no! If you do it Planck scales, then this not everything I said. It's completely. It doesn't work.
And then you have the usual problems with.
Then you have the usual problems. But I think the whole point was to find a problem at a scale which intermediate scale. Yeah, when the theory is weakly coupled, that's a tricky thing.
So would that be in low quantum gravity? Would you automatically be at Planck scale? Sorry for this question.
Planck scale.
Well, I would say in M theory, you'll be automatically. In M theory, there is no intermediate scales. Everything is Planck scale. And there is no intermediate scale regime. In low quantum gravity.
If I may ask, usually people give the argument for string theory by mentioning that gravity is non-normalizable and so on and so forth.
Exactly.
But here, even if we don't worry about that and just worry about effective quantum gravity, you are saying still there's evidence for higher spin. That is a fundamentally new argument, I would say. And in any motivation for string theory, you never hear the word causality, right? You always hear about the word UV completion.
Exactly, yes.
This goes beyond UV completion issue, right?
That's
Is
the
that
whole
right?
point. Right,
Yeah.
absolutely. So
I think this is brilliant because we can add to any colloquia on string theory now. This is one of the party
You
lines.
should first check our arguments.
No.
Because I think it's quite subtle.
Right? Okay. Now, quick second question. What about Masse's higher spin theory? Could that cure this problem?
Well, no, definitely. No, I think as soon as you have these massless particles which are very light, this computation that I did is
Not valid anymore.
it's not valid anymore. And I
So it's
think-
open question.
Yeah,
What's
yeah,
the
yeah,
theory, maybe causal, for all we know.
Yes. If you have, I think, I would bet that the theory is causal. Yes. But, well, because in higher spin phase, I think its boundary, its matrix is fixed. Be free. At least I think so.
No, I'm talking about broken high
The
space.
broken one, well, if it's dual to critical ON, it's physical
Again,
theory.
causal.
Yeah. If you, I think, but if you start in high spin theories, it's much harder to consider. I would say that, say, an open problem along these lines would be, let's consider Vasiliev theory and break high spin somehow, a little bit. So what are the allowed breakings and what are not? And in principle, maybe there is some of these breakings that will break causality. And then you say, I will rule out this kind of breakings. But I would bet that the Vasiliev one, it's a smart breaking, and it's good. It doesn't violate anything. But
That's not string theory.
sorry.
So Vasiliev theory is not equivalent to string theory.
Well, it's a subset of theory. You keep leading Reggie trajectory.
Right,
And it
but-
would be remarkable if that at least solves this problem. There could be other problems
Yeah.
which would require massive higher spins also,
Yeah,
even in
yeah.
Vasiliev. But it could be that this is not one of them.
Yeah. And again, also I think that say in Vasiliev theory, say to run this argument, one has to compute the shock wave in Vasiliev. And I don't know if it's known or not. Because I think if you know the shock wave, you can compute 4-point function. It will be just 2-point function in the shock wave background, which probably is doable. And this will be an example of first 4-point function computation with Vasiliev theory.
Indeed.
All right, let's next up again.